Well, what's that message? It's been a pain today. Okay, so we are starting a new chapter, chapter 12. So what we're going to deal with here is the 3D coordinate system and vectors. 3D coordinate system first. We'll do a few situations involving how we deal with 3D coordinates in calculus, in general in math. And then we'll move on to vectors in 3D. And so a lot of you will probably, if you've done anything with vectors, especially 3D vectors, are going to find a lot of overlap here, and that should make your life simpler. We also, this section in 12.2, the vector one, is the homework for this week, and the online test 6 still exists. We'll be on 12.1 and 12.2, so with a little bit of luck, your weekend will be a lot nicer than it typically is. So this here is a pretty standard diagram that you'll see in many textbooks for how you try and visualize something in 3D using 2D paper. So instead of just having our typical X and Y axis, which is what we would have if we were doing 2 dimensions, we add a third one, which is that. It's really trying to represent that, right? And then you kind of tilt it. Now, if you look carefully, you'll see that the orientation is rather weird, in my opinion anyway. This is positive x's, right? 1, 2, 3, 4. That's not so silly. 1, 2, 3, 4, I guess. And then Z, 1, 2, 3, 4. Obviously, it goes down the way with the negative values. But if you were trying to imagine what the X and Y looks like, you have to kind of turn it more like that to get an orientation that would look like 2 dimensions. Can you see the X and Y are pointing the way you'd expect them to? And this orientation, I believe, is called the right-hand rule, where the thumb is your Z. And here we go, X, Y, and Z. And it's orientated that way because of engineers. Evidently, engineers and physics people like the thing called the right-hand rule because they think you always point the right way, so the force field points up and not down. And that's what that's one of the reasons we do this. So if you want to give someone a coordinate like this one, it would be 3, 5, 10. So you start at the origin, 3 in the X, 5 in the Y, and vertically up 10. And that's how you do 3D coordinates if you're trying to plot them. Now, a couple of things. There is a 2D world that we are hopefully very comfortable with, and a 3D world that you might or might not be so comfortable with. And we're going to look at what does an equation look like and what do you get in a 2D world equation if you write the same equation down in 3D. Right. If I said, what does that look like in 2D? I hope you would say it's a vertical line passing through the x-axis at 5, right? So that's a line. It really represents all the points in 2D space that have the property that their x-coordinate is 5. Comfortable with that? If you do x equals 5 in 3D space, you do not get a line. What you get is a thing called a plane. And a plane is, well, it's not easy to do an is. So I'm going to show you on a piece of software what that looks like, because it is very visual. And I have a new piece of software called GeoBra that you'll find in Canvas. And I'll show you right now. So I'm saying the line x equals 5 is a plane. A plane is like a thin, infinitely thin sheet of paper, right? And it has the property that all the points on that piece of paper have an x coordinate of 5, but their y or z coordinates could be anything, right? I use looking at GeoBra right now. Is that the screen? Okay, so I'll just go up here, and I hope this works. been a while since I've used it. Hey, you see that light blue guy? Right, if you orientate it a little bit more, where the X goes this way and the Y goes that way, can you see the X equals 5? It's plain paper. Now, if I type in Y equals X squared, if you orientate all the points and I turn it, oh dear, shushed. Okay. I'm going to get dizzy doing this. It doesn't want to show me it right on, so let's go back to here. Can you imagine looking at the XY plane? Doesn't that look like Y equals X squared? But isn't it like a curved piece of paper, right? So can you see that in 3D you get plane, whereas in 2D it would be a curve or a line? You see there's a similarity, but also a difference. Now, if I type in, let's get rid of these guys, too many things going on. There we go. Don't know what that's doing now. If you do X squared plus Y squared equals, let's say, 4. Oops, I forgot to put my square. I thought I had. There. Can you see? Oh, there it's been. It disappeared on me. I'm having software issues. There we go. Does anybody know what we call this 3D surface?
That's a cylinder, right?
It is. It's called the cylinder.
Or a can.
No, I like the cylinder. That's the proper name, at least a math name, maybe not the proper name. We call that shape a cylinder. Now, in one orientation, can you see if you look at it? Oh, it's going to disappear. Before it disappeared, if I looked at it from above, straight down, wouldn't it just look like X squared plus Y squared equals 4? Because the grey, see that grey plane? That's actually called the XY plane, right? That's like the floor, right? And Z equals 0 generates that. And we have that guy. So we call them cylinders. Now, what would happen if I do X squared plus Z squared equals 4? That's what X squared plus Y squared equals 4. It's a cylinder that goes vertically upwards, right? It points in the direction of the Y-axis. But what would X squared plus Z squared equals 4 look like? X squared plus Z squared equals 4. Does it make sense that you'd get a cylinder, but you see the orientation is different? Now, the top one was a vertical cylinder. In other words, it pointed in the direction upwards, which is the Y-axis. This one here points along the Y-axis. So if I orientate this a little bit differently, can you see the Y-axis a little bit clearer? Now, only for completeness sake, if you do X squared, which one have I? No, I've done X squared. If you do Y squared plus X squared equals 4. Oh, I've done that one. Try to think of the one, the better way to. Can you see the 3 together? Does that give you an idea that when you move to the 3D world, equations take on another dimension? They have the basic shape of a circle, but now it becomes a cylinder. They look like a line, but if you really look at it, it becomes a plane. Now, the last one that I want to talk about is this one here. I'm going to do X squared plus Y squared plus Z squared equals 4. So X squared plus Y squared plus Z squared equals 4. What will that look like in 3D?
A circle or a sphere?
A sphere, yeah. In a way, isn't a sphere just a 3-dimensional version of a circle. Isn't that cool? Are you comfortable then if I gave you one of these types of equations, you could visualize it? So if I said, I've got a cylinder, x squared plus y squared equals 9. Do you see a vertical cylinder, radius 3? Right. If I said to you x equals 4, you'd get one. Now, I've only done x equals. You can actually do, and I hope it takes this one, but you're never quite sure how it's going to react. There we go. 2x plus 3y plus 5z equals a number. Do you see what you get is a diagonal plane? See it? That would be the equivalent of y equals 2x plus 1, you know, like a diagonal line. So it doesn't always have to be a vertical plane or a horizontal plane. If you do a combination of all three variables, don't you kind of get an angled plane instead? So I think that went pretty good. At least that's what I'm going for. So let's see what kind of things you would be asked. It's a very short section as far as homework questions go. So if you bear with me for a minute while I load up a couple. Right. I don't know what that is, but I want it to go away. So the first question it says is, what does x equal 3 look like? And the answer is it's a plane, and I will let you do that. Let's talk about some other situations. Suppose I have a point in 3D space, P. Imagine that's P. And I got another point up here in 3D space, that's Q. And maybe it's 5, -1, 7, right? Wouldn't it be helpful to find the length of the line joining P to Q? You know, now I know that looks 2D, but I'm not going to do an X, Y, Z axis. It's not worth the effort, right? Yeah, that's PQ, right? The top and the bottom of my pen, right? There's a formula that you may have heard. It's called the distance formula. Can you remember it? And the distance formula basically allows you to calculate the distance between 2 points. Now, in the 2D world, it would look something like this. The x coordinate of Q, take away x coordinate of P squared, plus the y coordinate of Q, take away the y coordinate of P squared, right? Sometimes it's called x2 take away x1 squared, y2 take away y1 squared, right? That's called the distance formula. How do you think you're going to extend it to find the distance between 2 points in 3D space?
ZQ minus CP.
Or even ZQ take away ZP. Yes. So in this question, obviously, let's see what that ends up being. I tend to just do it as second, take away the first, because it's easier in my brain. So 5 take away 1 is 4 squared. -1 take away 2 is -3 squared. 7 take away 3 is 4 squared. 16, 16, 32, 32 and 9, square root of 41. And normally we just leave things alone, right? That's the square root of 41. So if you know the coordinates in 3D space, can't you find the distance between any 2 points in 3D space by essentially using this formula? Now, once mathematicians moved from 2D world to 3D world, and they looked at some of the things they would do in the 2-dimensional and saw what happened to them in 3, like a line became a plane, it was nice that the formula for the distance between them really just was an extension. Would you agree it's just that guy, add one more? But once you've done that, if you want to really get into weirdness, couldn't you do the distance between 2 points in 4-dimensional space? Right? You'd have 4 coordinates, right? X, Y, Z, T, right? Wouldn't it be that one, that one, that one, and one more? Theoretically, couldn't you find the distance between 2 points in 11-dimensional space? There's no limit anymore. And the fact that the formula is consistent is very nice to mathematicians. Wouldn't it be horrible if every time you added the dimension, it was a totally weird, different formula every time? That would not be so pleasant. So one of the questions that you're going to get is 3 points. I'm not going to do the whole question because there's only one of them. But imagine you've got a point P, you've got a point Q, and you've got a point R. And the question asks you to find PQ, and then it asks you to find QR, and then it finally gets you to find RP. Now, if you just imagine that's P here, this is Q here, and this is R here. In 3D space, don't 3 points still make a triangle? Right, don't matter where you put them, right? When you join them up, you get a triangle, unless you pick 3 in a straight line. This guy is 3, this guy is 4, and this guy is 5, just for argument's sake. Is this triangle right angled?
Well, if we calculate the Pythagorean theorem, then yes.
And that's the answer, if that was the case, right? Suppose that was the lens. Is this one right angled? Yes.
I think so.
Check it out. Is 6 squared plus 6 squared that guy squared? And the answer is yes, there's 72. Is this triangle isosceles?
Oh, I was going to say it is isosceles first.
Right. So can't you be both? Right. That's isosceles because 2 sides are the same. Is it right angled? Yes. Right. So that is question 3, if you're wondering. That's what that's about. The last question I'm going to deal with is a sphere. We've very briefly touched on it.
Hey, would you mind putting that paper you just had on?
There you go.
Thank you.
X squared plus Y squared plus Z squared is a sphere, center of the origin, and it has a radius of 3. Agreed? And if that was 25, wouldn't it still have a center of the origin, but its radius would be 5? An extension of that, if you have a circle, there you go again. If you have a sphere and it's 1, 2, -3 is where the center is, and the radius of this sphere is 5, then the equation of that sphere becomes x minus 1 squared plus y take away 2 squared plus z add 3 squared equals 25. Does that make sense? If I went and said I had a circle in 2D space and it was 1, 2 and its radius is 5, wouldn't the answer look like that guy?
Yes, sir.
The center and the radius. So if I give you a point, -5, 4, 9. So this is me essentially doing question 4, or a version of it. And I told you that the radius was 9. And I asked you for the equation. Take that away, so you end up with x plus 5 squared. That's a normal 4, so y minus 4 squared. That's a normal 9. Z take away 9 squared equals 81.
So when we get a set of points like that, we treat it as y2 and x2 and z2.
Yeah, pretty much. So isn't it just an extension of what you would have done in 2D again, right? It's not a totally new formula, it's just a little bit added. But here's the kicker. That's question A, pretty much done. Question B says, what is the intersection of this sphere with what they call the XZ plane? So I'm going to return back, I've got it, to this picture so I can explain to you what the three planes are called. Add a couple of extra dotted lines there. The floor, I like to think of them as the floor and the walls, right? Just to visualize for me. The floor is called the XY plane. And the XY plane has an equation. It's called Z equals 0. Would you agree that everybody on the floor has a Z value of 0, right? A height of 0. Now, if you wanted to do this, picture is going to get wasted after I do this, so you only get one shot at doing it. Can you imagine that wall here? Right? This wall, what my hand is representing. That wall is called the XZ plane. Does its name make sense why it's called the XZ plane? Right, you're using the X and the Z axis. Now, in the XZ plane, all the Y coordinates are 0. Do you see that? Every single point on the XZ plane has the feature that it's Y. So the third one, which I'm not going to draw here, is going to be the YZ plane,
And
which would be the
0.
wall going. And say that again for me, please.
X will equal 0.
That will X equals 0. So if someone says to you the YZ plane, aren't they also telling you that the Z coordinate is 0? And if someone says the YZ plane, you know that they're talking about a plane with the equation X equals 0, right? So they're not different things. They're just different ways of saying the same thing. So now I'm going to go back to the second part of question 4. Here is the equation. Right? Here is the equation. Oh, that is interesting. Is that the right numbers? It is. Wow. I know what's going to happen and it's kind of weird, but I like it. If you do the intersection of the XZ plane, right? What's that the same thing as? X equals 0, Y equals 0, or Z equals 0?
Y equals 0, right?
Okay. Do you know it's the letter that it doesn't have? XZ doesn't have a Y, so Y equals 0. That's a quick way to remember it. Now, I'm going to use that by rewriting this equation, but replacing the Y by 0. Because essentially that's, can you imagine the 3D sphere being cut by the sidewall, right? The XZ plane. Now, when they intersect, doesn't a sphere make a circle when it hits a wall? Imagine somebody vertically cut it. Wouldn't that cut be a circle? So this should be a circle when I'm finished. So it's x plus 5 squared plus 0 take away 4 squared plus z take away 9 squared equals 81. So I have x plus 5 squared plus 16 plus z minus 9 squared equals 81. And I get that guy squared, oh, don't need that anymore, plus this guy squared and 65 and 65. So wouldn't you get a circle on the wall? -5, 9. And the radius would be the rather ugly square root of 65. So can you imagine this is the plane they're talking about? When the sphere meets it, won't it make it a little circle? And won't the center of that circle be there? And won't the radius of that circle be that?
Hey, why is a -5?
Why is this -5 and why is that +9?
Yeah.
When you do the equations of circles or anything, and there's this feature that when you move something, the opposite thing happens, equivalent. If I went and said to you, sketch those two things,
Oh, I got you.
that's the thing that's happening, right? If you move something, you change it to X minus the movement.
Oh, and one last thing. Like on right where your finger is, your right one, on the last line on the paper, why couldn't you just take the square root of it when it's still equal to 81 before you move the 16 over?
Because if you take the square root before you do a subtraction, you're doing them in the wrong order. Because you don't normally take the square root of this until after you've only got variables. If you did it before, well, I'm not even sure if you'd be allowed to do that. You can't call that x plus 5 plus 4 z minus 9 equals 9. Square roots don't work that way. You're not allowed to do a square root inside adding. The algebra doesn't work.
All right. Thank you.
That is the end of 12 Wonders. About 3 videos. It's a very visual thing, so videos are probably the best way to tackle those questions. But I think there's only about 8 questions, so it's not a huge workload either. So now we're going to do the second and last topic for today. It's going to be in section 12.2. We're going to do vectors, in particular 3D vectors. Now, some of you have done a lot of vectors. Jeremy, what was the name of that class you were talking about with the IGIs again?
Engineering statics.
Right. So if you've done statics, the statics, is there a 2D vector version of statics and then the next class is a 3D, or does statics do both the 2 and 3D?
They do them both.
Yeah, it's
Okay.
both at the same time.
Right. Which just kind of makes sense. Isn't it not that difficult to go from 2D vectors to 3D vectors? Now, some of you who've not done that class, then this will be a little bit more challenging for you, but hopefully not too much. So what we're looking at, and I'm going to do one of those attempts at making something look 3D and 2D paper. Imagine I've got a point here and it goes to a point here. So we'll call this P, we'll call this Q, and we do that. We call them a vector, right? That's a 3-dimensional vector. Can you imagine this pen? Right, there we go, is a vector in 3D. And so we're going to look at how to deal with vectors, how to add them, combine them, how you find the lengths of them, how you find unit vectors of them, you know, a whole load of essentially the algebra vectors. That is just a fancy name for how do you manipulate vectors, right? If P has the point 1, 2, 5, that's this guy, and Q has the point 7, 8, 9, then there is a number of notations that you use to represent a vector. One of them is you give the start and finish letter and you put an arrow above it. Have you seen that in your statics? You can also, I don't know why they do this. Do you do a kind of half arrow? I've seen that notation being used. Have you seen that one?
I've seen it. Depends on who's doing it.
Right. So that and that are the same thing, right? You also sometimes have just a little letter of the alphabet, in this case U, and you put a little arrow above it, or you put a little U and you put half an arrow above it. I guess the answer is depends who's doing it, right? there's quite a lot of different notations for the same guy, right? Now, the last one is the one you're most likely to see in textbooks, and the one we never do on paper, and it's because it's so hard to draw. Don't you just get the letter U, but it's in bold? You seen that? That is also the same guy as the others, right? Since it's very difficult and annoying to try and do bold, can you see why we never do that on paper? You might see it in textbooks, but human beings don't like doing that. Out of all those choices, I'm going to use those two because I want to, and that's what I'm used to. And if the professor you got used those two, feel totally free to use them, right? It's the same thing, don't matter to me. So how do I find the vector? It's 3 numbers. A vector is, in 3D, 3 numbers. The first number is called the x component. The second number is called the y component of the vector. Not surprising, the third one is called the z component. So what you do with a vector is you start anywhere in 3D space, and then if it says 2, 3, 4, you go 2 in the x, 3 in the y, 4 in the z. And you start and you finish, and you join from where you start to where you finish, and that would be your vector. The equation or the formula for finding this guy, well, I'm going to call this guy xp, yp, zp, because that's his coordinates. And this is going to be xq, yq, zq, because that's his coordinates. The vector pq is given by xq take away xp, comma, yq take away yp, comma, zq take away zp. Does that formula make sense, that you just find the difference between the x, y, and z coordinates? And do you notice it's the second guy take away the first? You might say, well, can I just switch places and does it really matter? It does. If you switch these round, you're not getting the vector PQ, you're getting the vector QP. And vectors have a direction to them, right? A scalar is a number, but a vector has a direction to it. And if you get the wrong direction, it's a bit like me saying the answer is 42 when it should have been negative 42. Sure, it's got the 42 in it, but isn't that negative important? Right? You need to be precise. So in the question I've got here, this is kind of how I do it. I don't really use the formula. I just do this 2 take away 1 thing because it works for me. 7 take away 1 is 6. 8 take away 2 is 6. 9 take away 5 is 4. You see, when you do it that way, it's really quick, isn't it? 7 take away 1, right? Second take away first, second take away first, second take away first. And there is your vector. So if I give you 2 points in 3D space, are you comfortable that you can do the vector joining? That seems straightforward.
Yes, sir.
Cool. Right. Again, for those who've done vectors, this is baby stuff, right? You could do this in your sleep, but not for everyone because you've not all done vectors. Suppose I have a vector PQ and it's 1, -3, 4. And I would like to know what's called the magnitude of a vector. Magnitude is just a word that means the length of the vector. The reason why they sometimes use the word magnitude is very often vectors are used to represent forces pulling something or pushing something, right? And so you might talk about the magnitude of the force, meaning, right, are you pulling it with 42 newtons or 4 million newtons, right? Because that could make a big difference. So the magnitude or the length of a vector is simply, well, let me generalize this one and just call this guy ABC, right? So it represents any vector. It's a squared plus b squared plus c squared. In fact, if you make that a, that b, and that c, don't you have the distance formula? So they can overlap quite nicely.
So for sine gauge, we're not going to use the Cartesian notation.
What was that, Lewis? In sine gauge, what notation?
Cartesian, I think that's how it's called. The I, J, and K.
Oh, we haven't got to the IJKs. We will. Actually, why not do it now? Me personally, I like this notation. Right. I know it looks like greater than and less than symbols. I should have mentioned that. It's kind of obvious that's what they look like, but they're not. They're nothing to do with them. When I take over the world, I'm going to invent a new bracket symbol, and we'll use that when we do vectors, right? But until then, you got to live with it. I guess there's only so many things on a keyboard, so hey, let's use them, right? Aren't those guys already used up? Aren't they, for coordinates? So you couldn't use that one. Those guys are used up because guess what? Don't we use them in set builder notation? Aren't those guys used up because don't we use them in intervals? Can you see they were running shorty things? Let's use the less than and greater than symbol. Nobody's using that, right? We'll use it. And they got in first. If someone discovers a new branch of math, we're going to have a problem, aren't we? Because all the good ones are used up. You know, who knows what they'll use, you know, if somebody comes up with something else.
Will they use those symbols in the homework?
I hope you can. Why don't you try one question using them? They do have them in WebAssign, right? There is a place to go. As soon as I've shown you the IJK, I'm going to nip over to WebAssign and show you where to get them. Because your temptation when you do IJ notation is just to use the keyboard IJK, and it doesn't work, right? There's special buttons that you need. So there are 3 very special vectors called IJK notation. That's at least my name for it. That are used in vectors quite a lot. I don't like the notation, but it is used, so you should know how to do it. I is actually one movement in only the x direction. J is 1 unit of movement in the y direction, and k is 1 unit of movement in the z direction. So you see this vector here that I had a few moments ago, which was what, 1, -3, 4. If you wanted to do that in IJK notation, it would, oops, there I go. 1i, take away 3j plus 4k. Would you agree that they're totally equivalent, right? They're just different ways of saying the same thing, right? Are we good with that? That's IJ. Me personally, I almost always turn everything into this notation. So if you get me for Calc 4, you'll find when we do vectors, I exclusively use this, right? If you like IJK, cool. I don't mind, it works. So let's nip over and see where they have all the things to make your answer ham. So there, I'm going to click on this guy and I'm going to go to vectors. And you see my funny little bracket guy? So I know this isn't the answer, but there. Do you see how you type in 1, 2, 3? Right? Do you notice that you use that top right-hand corner guy, right? If you just typed in less than symbol, 1, 2, 3, greater than symbol, I mean, it would look like it is what I've just written. Would you agree? WebAssign will say, don't know what you mean, you're wrong. Now, IJK notation is also here. If you wanted to do this vector 1, 2, 3, you would do 1i plus 2j plus 3j Okay. If you just typed in I plus j, or I plus 2j plus 3k, it looks very similar, doesn't it? It looks like you're typing in the answer, but WebAssign again will ding you, right? So when you're doing anything on the vectors, this menu here, the sub menu, is going to be your go-to guy. Now, I don't know why it's got a square root there. Well, I guess if you wanted the distance formula, the square root being there is kind of helpful, isn't it? Because you're doing all the vector stuff. But the ones you're really interested in, I should say, is these guys here. Oh, there's your little arrow. If you want to do PQ, guess I should try that one. Right, I don't want that one, go away. Here we go. Do you do it first? I've never tried the PQ one, let me try it. Vectors. I think you do PQ, it's always capitals, PQ, and then you hit the arrow button. Nope, okay. Then you hit the arrow button, and then you do PQ. There, that's how you get the arrows. Are we okay about how you get your answer into WebAssign, right? IJK notation or component form, right? Component form, when I use that term, I mean the bracket, you guys. IJK notation, I think that's pretty clear what I'm talking about. So far, so good? Right, so let's return to notes. And let's look at what seems a reasonable request. And that is, well, if you've got vectors, how do you add them? How do you subtract them? Can you multiply them? What situations can you? Right. Well, let's suppose I have a vector A, 1, 3, -2, and I have a vector B, 2, 4, -1, and a vector C, 0, -2, 5. Right. You can add and subtract two vectors together. There's the first vector, and here's the second vector. If you've never done vectors in your life before, would it make sense that the most obvious way to add two vectors is just add their x components, add their y components, and add their z components? Would that make sense? So you would add, and add. And in this case, 3, 7, -3. Now, if you want to visualize what that's like, can you imagine in 3D, this is what the vector A looks like. And it starts here and it finishes here. And where it finishes, you then do the vector B. And can you imagine that's what vector B looks like? When you add two vectors together, you do this nose to tail thing. And if you take the start of the journey and the end of the journey, you make a little triangle. And that's what the vector A plus B would look like. Geometrically, that's kind of elegant, isn't it? That if you want to add two vectors together, the sum is just a vector that takes you from the beginning of the journey to the end. Now you can do what are called scalar multiples of vectors. A scalar multiple would be something like 3a. Now that would be 3 times whatever a happens to be in this case. That's a. Again, if you've never done vectors before, won't it make sense that the simplest way to understand what this is doing would be to treble the components? Would that make sense? Each one would get multiplied by 3, in which case you would get the vector 3, 9, -6. And that's what the vector 3a looks like. Now you want to visualize what does that look geometrically? Can you imagine that's what vector A looks like? Wouldn't vector 3a, well, I hope it would look sensible. Wouldn't it be the same direction, right? Parallel to A, just 3 times longer. Does that make sense? So let's do strange multiple. Just negative of A. It's actually called the negative of the vector A. So here is my vector A. If you find the negative of it, that's what your answer looks like in component form, right? Negative 3. If I put it in the right place, yeah. Negative 1, negative 3, and positive 2. Does that make sense? Intuitive? Now, if this is A, what would the vector negative A look like?
Totally opposite from the vector A.
Do you see the only difference is orientation? A, negative A. That makes sense? Visually, with that kind of intuitive? Yeah. Can you see why vectors are so helpful in modeling forces, especially, right? Any kind of movement, any kind of force. Because when you think about a force, don't you have a direction to it, right? Am I pushing the box or am I pulling the box, right? Am I trying to lift it off the ground or am I trying to push it into the ground, right? There's a direction associated with every vector, right? And so it's useful that we have a math method of representing that physical situation. So vectors get used a lot in architecture where you're trying to figure out what are the forces acting on a girder or in almost anything, right? In the engineering world. Can you imagine vectors could play a part in modeling what's going on? So we want to be able to, you know, manipulate. Pretty simple manipulation right now, but we will come to more complicated ones. There's a special vector called the zero vector. What are the components of the zero vector?
This is a 0. It has 0, 0, and 0 inside of it, right?
Right. If you try and draw the zero vector, you don't get much. Isn't it just a point in space? Now, that's the only vector in the universe that has 0 magnitude. In other words, its length is 0. Don't all of them have a length? Because basically, isn't that saying no force, that's just a place in space, right? That's it. Now, why is the zero vector helpful? Very often when you construct things, you want to balance the forces, right? So you've got a big pole and there's lots of forces pulling it this way and that way. But you want to keep the pole vertical. Wouldn't you want to know one vector that would balance it? Right, so if all the forces make 1, 2, 3, don't you just make the balancing force -1, -2, -3, in which case that's the force that you would have to pull. It would be the direction that you'd need to pull, and it would even tell you how long, right, the force, the magnitude. And so you can keep things balanced, which is something that you tend to want to be true in many cases. So let's do the algebra of vectors. What I mean by that is, well, let's use this guy because I spent all my time writing them down. I haven't even used them yet. Right. So for this fella here, we'll get in a minute. There you go. Move this out of the way. The algebra of vectors is basically just any kind of calculation, right? Manipulation of these. So you might be asked, and this is some of the things you could be asked, to calculate that vector. You might be asked to calculate the magnitude of that vector. Just 2 examples. The kind of question that I'm talking about right now is question 2, which kind of qualify as that. Well, based on my example here, 3 times this vector. I don't need these brackets actually. 2 times this vector. Take away this vector. Now, the brave amongst you could do that in one go, but I'm going to be a little bit more conservative. Got that guy. Got that guy. I don't like negatives, so couldn't I just do that? Right. So the negative of that is this vector. And now I can add them in my head. 3 add 4 add nothing gets me 7. 9 add 8 is 17, and 2 makes 19. Negative 6, negative 2 is negative 8, oh, negative 13. Are you comfortable with any linear combination, any scalar multiple added together, subtracted? You could do it. Does that seem reasonable? Once you've seen one, you've seen them all. Now, if you're being asked to find, this is, I guess, question B. If you're being asked to find the magnitude of 2a plus 3c, first you find what that vector is, and then you get its magnitude. So I do it in 2 parts. I find out what the components of this guy are. So 2 times a, well, that's a, so it's 2 times this guy, plus 3 times this guy. And this guy is 2, 6, negative 4. And this guy is 0, negative 6, and 15. And if you add them together, you get 2, you get a 0, and you get an 11. So far, so good. And to get the magnitude of this vector, don't we just 2 squared, nothing squared, 11 squared. Remember the formula for getting the magnitude of a vector? A squared plus b squared plus c squared. So what that'd be 4, 0, 121, square root of 125. Ooh, that's interesting. 5 root 5. A little bit quick, we good? Right, get nods, I like nods. So next thing we're going to look at is a vector called the unit vector. With the exception of the 0 vector.
Could I see that? Could you place that paper on the back up?
With the exception of the 0 vector, you can get a unit vector. Let's show you what it looks like. Can we imagine this vector is A? The unit vector is a vector parallel to it. Let's call it U for unit vector. And it has the property that its magnitude is 1. So a unit vector is a vector parallel to the given vector, but whose length is 1, right? Whose magnitude is 1. And we can calculate unit vectors. And this is how you would do it. Suppose you had 5, 1, 2. I'll make that negative, right? I would like to calculate the unit vector for this vector. First thing you do is you must find the magnitude of vector A. So it's going to be 5 squared, 1 squared, negative 2 squared, 25, 26, 30, square root of 30. And the unit vector then is basically 1 over the magnitude of A, so that's a fraction, of the original vector A. So that's going to be 1 over root 30, this vector. And we don't like vectors written like this. For style points, they should all be inside. Oops, there's a 3 there. That vector is parallel to A. How is it parallel? Because any multiple of A is parallel to it, right? But because I've divided by its length, do you see that that guy will have, if I found the magnitude of this guy, wouldn't its length be 1? Does that make sense? You check out that squared plus that squared plus that squared ends up being 30/30ths, which is 1. You're looking puzzled. What's the problem, Caitlin? Are we have a problem, or are you just thinking hard?
I think I was writing it all down and I think I got lost, so I'll figure it out.
Okay, I was probably going too quick. So here is the original question. There is its magnitude, right? 5 squared, 1 squared, -2 squared, which is the square root of 30. The formula for the unit vector is 1 over the magnitude of the vector A. So 1 over the square root of 30 of the vector A. And that's just a multiple. I know you're used to 2 and 3, but a half and 1/90th is also multiples. So if you multiply the scalar through, you get 5 over root 30, 1 over root 30, -2 over root 30. That says root 30, it's a mess, but it is. And that's called a unit vector. And unit vectors are sometimes useful. They give you an idea of the direction without getting too complicated about how long it is, right? You don't want big, long vectors and little skinny ones. You're just basically interested in the direction. So a unit vector is a good standardized way that you can give a direction. Now there is a more subtle version of that. Let's change letters. The vector B is 3, 4, -1, right? And I want a vector parallel to the vector V, but whose magnitude is whatever they ask it. So let's say whose magnitude is 10, right? So can you imagine this is vector B, and it doesn't need to be a unit letter, but can you imagine I want this vector here to be parallel to this guy, but I want this to be 10 units long, right? Magnitude of 10, right? Maybe this is 4, right? But I want somebody who's 10, right? That's the puzzle. So this is how you solve it. First thing you do is find the unit vector of B. And then something else is going to happen, but I'll leave that blank for the time being. Well, if I want to find the magnitude of vector B, it's the square root of 3 squared plus 4 squared plus -1 squared. So that's square root of 26. So the unit vector would be 1 over square root of 26. That's what makes it a unit vector of this guy. And that gets me a really ugly looking vector whose components are 3 over the square root of 26, 4 over the square root of 26, and -1 over the square root of 26. Essentially, I got that guy there, right? But I don't want the unit vector. I don't want a vector parallel to him who's 1 unit long. I want a guy that's parallel to him that's 10 units long. So the second step is you multiply the unit vector by what?
Whatever magnitude you want.
Yeah, in this case I want 10, so I'll multiply it by 10. Maybe the next time I want it to be, you know, half a unit long, 2 million units long. So you see that you still find a unit vector, but then you do something, right? That's the only difference between find a unit vector and find somebody that's parallel to me, but with a given length. So I don't know what to call this vector, so I'll call it C, right? So we're going to find this vector C, and he is going to be, or she, if it's a female, is going to be this guy. So 30 out of the square root of 26, 40 out of the square root of 26, and negative 10 out of the square root of 26. Now, sometimes WebAssign will phrase the question like that. Sometimes they will tell you that B is 3i plus 4j minus 1k, right? And ask you the same question. Now, there are two ways to do that. You can just go through the same process using ijk, which is fine. Or you turn it into this guy, you get the answer, and then can't you just rewrite the answer as that many i's plus that many j's, take away that many k's. Or if WebAssign is being really nice to you, won't it accept that answer and you won't need to do the conversion at all? I have no idea. My gut feeling is that WebAssign is going to be awkward, in which case, if it gives you ijk's, it wants them. But that's just a gut feeling. I could easily be wrong. How are we doing, guys? Right, the people who've done vectors before, is this pretty much the same way that you would have done the same kind of questions? There's nothing, I'm not doing it weird. Kinda? What's the difference that you noticed, Tom, Thomas?
I did the vectors a little differently. But I was in.
Right. Is it something major, or you can live with the way I do it, or you can just adapt
I can live
how
with
you
it.
do it?
It's
Okay.
fine.
Right. I don't like what's the word I'm looking for? I'm in engineer world right now, okay? Which means I have to be respectful of how engineers would do things. And I don't want to, you know, do something and then an engineer comes and says, Donald, I wish you hadn't done vectors that way, because that really confuses this other thing that I'm going to do where, okay, the math people, it works fine, but for us, we need to look at it a different way, you know, the left-hand rule, right-hand rule, whatever it is going to be, and your way is just going to, you know. Isn't it sometimes worse to have the wrong idea than to have no idea, right? And, you know, unlearning something can be a bit of a pain, especially if it makes sense the first time round. How are we doing so far, guys? Cool. I'm trying to think of anything that I may have missed. I think I've done all the obvious stuff in the vectors, although I didn't have enough time to add to these questions, but hold on just a moment. All right, where are we? Come on, 12. I think I've covered everything, but I've got a feeling I might have missed one thing. And it might be in applications. So if you can bear with me, I'm trying to load it up and go right to the bottom in case I did. No, that's 2D applications. I'm not interested in 2D. No, that's 2D applications. Still not interested. Yeah, okay, I'm wrong. We have covered pretty much everything that you need for the first two sections. So I'll get a head start on the next section. You only need 12.1 and 12.2 for the homework. You only need 12.1 and 12.2 for the test, but here's 12.3. So it's section 12.3, and it's called the dot product. So imagine I have two vectors, one called u, and we're going to call its components u1, u2, and u3. And I have a second vector v, and I'm going to call its components v1, v2, and v3. There is an operation on vectors called the dot product. Now, there is another name for it. I might mention it. If you haven't heard it, then I'll skip right by it. Have you ever heard it called the scalar product? So the vector people call it dot product, right? Engineer people, right? Great. So it's a dot product. Forget the other term. Unless you happen to be watching a video and the guy says scalar product, well, you just say, just another name for dot product, right? That's all it is, just another name, right? So the dot product of the vectors u and v, written as u dot v. That's how you say it out loud. U dot v is equal to u1 v1 plus u2 v2 plus u3 v3. You can see why it's got the name product, aren't you, multiplying things together? Aren't you essentially multiplying the x, the y, and the z components together and adding them? So for instance, if u was the vector 1, 2, -3, and v was the vector 5, -1, 0, then the dot product would be 1 times 5 plus 2 times -1 plus -3 times 0. And that's 5, and that's -2, and that's nothing. So the answer is 3. So you might think, okay, there's a guy called the dot product. What can I use it for? The vector people amongst us, what's the main use for a dot product? What does it tell you about the two vectors u and v? So imagine this is u going this way. Imagine this is v going that way. What does the dot product allow you to calculate? Come on, guys, you've taken the class. I know you know the answer to this.
The main use of the dot product is to torture students.
After that, the second usage then. Oh, come on, I'm getting old here. You know, every minute is worthwhile for me. Make it useful. Tell me something. It allows you to find the angle between two vectors. That's what the dot product's main usage is, right? Because if you have a vector pulling this way and a vector pulling that way, wouldn't you like to know the angle between them? It would be a useful thing to know. Now that I've told you that, oops, that's a u. U dot v divided by the magnitude of u times the magnitude of v. What is that equal to? Can someone remember that? Because you actually did it in 142 as well.
Cosine.
Correct. So the cosine of the angle theta between the two vectors is that. So since I've got these two vectors set up, let's find the angle between these two vectors, right? Is it 40 degrees? Is it 140 degrees, right? Whatever it's going to be. So the dot product I've already calculated, so I'll put that down as 3. The magnitude of the vectors, well, I'll just do that right now. It's 1 squared plus 2 squared plus -3 squared. That's the first one. And the magnitude of the second vector is the square root of 5 squared plus -1 squared plus 0 squared. So that's going to be 3, 9, 10 square root of 14, 25, 26 times, so times there. So at that point, I would basically get my calculator. What should I do to both sides to find the angle theta? I know the cosine of theta is this ugly fraction. What would I get? Or
Inverse
how would I
cosine.
get? Right, inverse cosine. Now, the advantage of leaving everything kind of at its exact values is that when you come to do the calculator, can't you just do it all in one big ugly dot, rather than individually getting square roots of this and so on. So inverse cosine coming up, and it's 3 on the top, divided by, I'm now going to do a deliberate mistake. Oh, it's the square root of 14 times it's the square root of 26. Yep.
Hey, you should be a engineering teacher because my teacher did not explain this to us this way.
I'm not sure that's a good sign. It probably means I've missed a whole load of stuff that the engineers find important. Right.
He just gave us the formulas. He said plug and chug and have a good day.
Okay, well, then I haven't missed anything. So I'm bringing this guy back up. Can anybody see what was wrong with the calculation? It looks like it's right. Okay, 3 and the 2 square roots.
Well, the calculation was wrong because that is actually 3 divided by square root of 14 times square root of 26. Is that right?
Yes. So order of calculation is a problem. If you want to do one of these in one go, you do 3 divided by, and then you have to stick an extra bracket in. And that gets it to do these 2 square roots the way and the order that you wanted them to be done. In other words, you wanted these 2 guys to be done together, right? Now, if I hit
Cosine square
enter,
root 26.
so in this case, 79.67.
Question, are you in
20.
degree or are you in radian?
I better check. I think I'm in degrees. Yes, I am.
That is really why I got 1.41.
Yeah, unless the question specifies otherwise. Degrees are much more helpful in these questions. Would you agree? You can imagine 79.67 degrees. It's not that easy to imagine 1.5 radians, right? I don't know how big that is. Is it that big or is it that big? You know, 679. Yeah, I got a good picture of it. Are we comfortable then that if I give you 2 vectors, that you could find the angle between those 2 vectors? Okay. So let's do a special case of finding the angle between 2 vectors, right? Here's my new vectors. 3, 1, 2. And my vector V is 5, 2, -19. Yeah. Now I'm only going to calculate the dot product. So it's going to be 3 times 5 plus 1 times -19 plus 2 times 2. And can you trust me that the answer is 0? If the dot product is 0 and the vectors that you used weren't the 0 vector, right? Because that's a trivial situation. We can say something quite interesting about the angle between these 2 vectors. What angle do you think is going to be between those 2 vectors? Even although I'm not going to do the rest of the calculation, because I know what it's going to be.
90.
It's going to be 90. Now, if you go through the work, isn't it going to be 0 over a whole load of square roots? But isn't 0 over a whole load of square roots still 0? And isn't the inverse cosine of 0 90 degrees? So what we have here is a very quick test for our two vectors at right angles. So can you imagine this is one and this is the other? Pretty cool. Dot product. Now, 90 degrees is fine. You could say that, oops, not there, that the two vectors are at right angles or right angled, right angles. Have you used that phrase in the vector world? Two vectors are at right angles? Or have you used this one? Two vectors are orthogonal. Have any of you heard that term? Orthogonal. Right, I get one nod. That's not a good sign. Do you remember it, or you think you've heard it and forgot about it, or is it never heard that word in my life before? Orthogonal. Any
Does it mean
volunteers?
90%, 90 degrees?
Yeah, just another name for right 90 degrees. Now, why do we have this word? Why do we even need it when 90 degrees in right angled works? This is more for the mathematics people. We deal, well, engineers deal with 3 dimensions in real life, right? If you're building a tunnel, you just need to know 3 dimensions, right? If you're doing a spaceship, you could argue a spaceship's slightly different, but if you're doing something like a rocket, 3 dimensions is fine, right? Takes care of the world as we typically live it. But when you go into 4 dimensions, because we know that you can do 4-dimensional vectors, can't you? Can you just write them down? You can find the angle between 2 4-dimensional vectors, but it stops being visual, right? We live in the 3. We don't live in the 4 dimensions. So it's not a good idea to say something's right angled if it's a 4th-dimensional vector. It's much better just to call it orthogonal. And then you don't need to worry about, well, what does it look like? The short answer is I don't think anybody knows what a 4th-dimensional vector that's orthogonal to another one is. I mean, you can't visualize a 4th-dimensional vector anyway. If you want to get your head hurting, go looking online for an object called a hypercube. There's a video of it, hypercube. And a hypercube is a representation of what a 4th-dimensional cube would look like. And it's painful. It just, you'll hurt your brain. So a little side issue, we being mathematicians, we extend the world beyond 3 dimensions because we can. Engineers say, don't be so stupid. 3 dimensions is the world. Why should anybody ever want to do more? Because it's not going to help us. The only reason I kind of changed my mind slightly is that if you are doing a spaceship and you are flying, space-time is 4-dimensional. When they do things moving in very fast speeds or are subjected to extreme gravity, the 4th dimension space-time actually kicks in. It actually does mean that the spaceship doesn't quite travel the way it would travel if the world was truly 3-dimensional. So,
Professor,
but,
I just had a
yes.
question. For finding cosine, like, is the reason we couldn't have just divided the magnitude of u by the magnitude of v is because we didn't know if it was a right triangle to begin with? Like for like adjacent over hypotenuse, the cosine.
Oh yeah, because you don't know the angle, you can't make that assumption. The fact that this one happened to be right angled, most of them won't be, so you can't just say that's opposite over adjacent or whatever, because there's no, you don't know that that's right angled. In fact, it probably isn't, so you can't really do opposite over adjacent anyway. I think we've reached a nice finishing point, haven't we?
Yes, sir.
And when you go and talk to you, who does vectors? What professors in engineering have you done vectors with? Just curious.
Dunkel.
Okay. So when you talk to him, you will not say to him, well, I had a class with Mr. Robertson and he done vectors a weird way and he went and said that he was right and you were wrong. Because I never at any point said that. In fact, I think I said the opposite, which is that I hope I
can't
don't
quote
do
you on
things
that?
the wrong way.
So we can't quote you on that one?
No, you definitely cannot
No,
quote
no,
me
it's
on that one.
implied. It's just implied. Yeah, you got it
Yeah.
right.
No, it's not. I'm not implying, suggesting, or anything else. I'm just saying that mathematicians sometimes look at the bigger picture because we can, but an engineer would only really want to live in the 3D world because that's what the world is. Okay, last name and bye-bye. I'll hang about for any questions. Everybody should have been given a report. Look at your email, find it. If you can't find it, shoot me an email and I will send you the report again using that email. The one that I used was either your OC email or the email that you used when you logged into WebAssign, right? Oh, bye-bye, guys. Oh.
Thank you.
Does anyone want to hear a joke?
I would love to hear a joke. Go for it.
Why don't left-hand people be engineer?
I don't know why left-hand people are not engineers.
Because engineer draw things in right hand.
Oh, the right-hand rule? Oh, God. Is that an engineer joke?
No, it's just the thing that I just picked up from this today's lecture.
Okay. Does anybody know when I do this with my thumb and three fingers what I'm talking about? You have no idea. Right, if you do, I believe that's two different places where the left and the right hand rule apply. One of them is in electromagnets, right? So one of your fingers is pointing in the direction of the current, one of them's pointing in the direction of the coil, and the third one is which way the north is. So it's either the left or the right hand rule, and there's another one that you use that to do with forces. So one day you will find out about the left and right hand rule, and you will remember that I told you it first, even if I got it back to front. Okay.
But I had a joke for you. I'm sorry I didn't put one on my homework. Like
it wouldn't have helped. Just grading that drove me crazy. Not yours in particular, just the fact of
Sorry.
grading all of them. You should be. Right, go for it. What's your joke?
So a wife goes to visit her husband in jail. And after she's done visiting him, she comes up to the guards and said, you know, you shouldn't be working my husband so hard. And the guy goes, what do you mean? All he does is just sits around and sleep. And the wife says, well, he told me he's been working on a tunnel for the last 6 months.
Oh God. Is this what we're down to now? I think my bad jokes are having a bad effect on my students. That's all I can think. Oh God, that is painful.
So you
Okay.
talk about my grades real quick, or
Yes, whatever. Yeah, sure.
I'm looking at online test 3. It says 11.
Let me look at it. Online test 3 says 11. That's a
Bye-bye,
strange number.
Professor.
Bye-bye. Give me a few moments to find your grade.
Or do you think it's just a typo in the thing?
I
In the,
hope it's. I'll be able to tell you. I copied it from the thing, so that shouldn't be the case. But you never know.
because it's still 89%.
So it sounds like it hasn't had any effect on the grade.
No, because it's 17, 97, 11, and 100.
Okay. Online test 3. Right. I'm almost there. Let's find out since they're passed. Yeah, that is the right grade, according to what I have here.
I got an 11 on it. I don't.
Yeah, I'm clicking on it right now. You only done 2 questions.
Only test
Yeah.
3?
Yeah.
I swore I did more because I stayed up that night.
I couldn't tell you when would week 3 be.
Was
2 weeks ago.
yeah.
But did you? All I can say is maybe you forgot to hit the button at the end that say submit.
Yeah, I'm checking it right.
You're allowed to drop 2. That's why it didn't affect your grade, because it was one of the 2 that get dropped. I bet you.
Oh, but at the same time, I'm not gonna lie to you. That's an embarrassment to me.
Right. It's kind of over with. There's not really much I can do now, unfortunately.
Yeah, I just for my sake.
So yeah, make sure hit submit. That's one of the most common mistakes. Sometimes what happens is that you're not careful with your time and it times you out before you're finished, and it can catch you that way as well. So that might have been one of those, might have been the reason that what happened. Okay, any other questions?
Yes.
No.
I have a question.
Yeah, Evan.
I've never seen this cosine theta formula before. Is it easy to prove it or derive it? And why isn't there one for sine of theta?
Well, the first one, it's not easy to prove it because you have to do quite messy math, but you can always, like everything, watch a video on it, just put down the proof of the dot product and see what pops up. Why has it not got a sign in it? The answer is not very good. It doesn't have a sign in it because it has a cosine in it. That's what the formula
No,
generates.
like is there a version where sine theta?
No, there
equals
isn't a
some-
sine version.
Okay.
Is it from the law of cosines or something?
Say again, Jeremy?
Is it from the law of cosines?
Partly, yes. I'm pretty sure, although it's a while since I've even looked at the proof or even tried it, but my gut feeling is yes, it's probably connected to the law of cosines. You've got your a squared plus b squared minus c thing going on. I think it's not directly connected to that, but I'm pretty sure that they use the cosine rule in the proof. But the thing is a 3D thing, and the cosine rule that you would use in 142 is a 2D thing, right? You only use it for 2-dimensional space. So it's not an exact one-for-one deal, but I'm pretty sure they use the cosine rule as part of the process of solving it.